recording. Today we have Bibek Upadhayay with us to present his work as part of his research at SAIL on combating human trafficking via automatic intelligence collection, validation, and fusion. Bibek has been a member of my research lab from almost the founding of the lab. He's a graduate student in the MS Computer Masters of Computer Science program and a research assistant at the Secure and Assured Intelligent Learning Lab. He is also the recipient of the 2020 to 2021 TCOE Graduate Research Fellowship. Bibek's research is on machine learning applications to fake news detection in online social media, and his work on this project has so far led to the curation of an open source dataset of fake claims called Sentimental Liar, as well as a novel deep learning approach to the classification of fake news in short texts, which has been published in a recent paper titled Sentimental Liar, Extended Corpus and Deep Learning Models for Fake Claim Classification. And this paper, I believe, was published in IEEE ISI last year. Bibek has also been working on combating human trafficking and cyber threat intelligence projects as part of his research work at SAIL. Bibek, thank you very much for accepting our invitation, and the floor is yours.
Thank you, Dr. Vaid. Thank you for the introduction. Hello, everyone. I'm Bibek Upadhayay from Cell Lab of University of New Haven. Today, I'm here to present this project with my colleague Jisan Ahmad and supervisor Dr. Vaid Behzadan himself. The project is on combating human trafficking via automatic intelligence collection, validation, and fusion. First, let's start with what is human trafficking. As we know the name what human trafficking is, but we also need to know why we're working on this area, because this is one of the major problems, major social problems. And it always have been, but now we can see the data of how many people are being trafficking. There has been a significant number of people being trafficked, 24.9 million, in which even the women only in which the women are 49%, children are 13%. That's the number of victims, as well as the men are also being trafficked in a daily basis. We need to know that how people are being trafficked, right? So most people move from their habitat willingly because they are in the motivation to search for better life because of the poverty or natural disaster, or if the area is war affected. But what happened is that when they traffic from one place to other, traffickers pursue them with hope of a better life, and then they get exploited. There are many forms of exploitation after the trafficking, including sexual exploitation, begging, forced labor, and many others. But what can we do, right? So we can look into this as in two aspects. In the first aspect is basically the policies that the government creates and the law information or an organization enforce those regulations that try to restrain traffickers and try to rescue the victims. That's at the top level. And we also need to look into the second aspect of it, what we can do as a community, right? So as a community, at the community level, we can mitigate the root cause of human trafficking and stop people in the first place from being a victim, so that the first aspect shouldn't be done at all. So in order to do that, we need to analyze each and every case individually, the previous cases, so that it will help us to analyze what was the root cause of the trafficking at all. So hence, we need to have a proper data in order to achieve this. The problem is that the NGOs and INGOs lack sufficient and timely data that has been working on the community. That's why Love Justice International, Cell Lab, and the Center for Forensic Investigation of Trafficking in Person at UNS initiated this project that has the aim to leverage the AI and machine learning methods in order to automate this whole process. But the current bottlenecks are the limitation of human analysis when they produce that intelligent data from the unstructured data and semi-structured data. And the other bottleneck is that the overhead of data flow and data integration in analytic pipelines. And how can we resolve those, right? So that's why you propose a system to leverage recent advances in information retrieval and machine learning in order to develop a prototype system that will address a specific manifestation of above mentioned limitation. How can we do this? So basically, we have summarized our whole work in 3 stages. In first stage, we are making a multi-source OSINT collector that basically crawls the internet and collect news that are related to the human trafficking, labor trafficking, and then we populate the case information form field. So what is case information form field? It is basically the field that has the name of the victims and all those metadata of the victims, like the nationality, their age, their gender, what were their education was, and what were the suspect who were identified as a suspect. So those kind of things in order to present an article that is related to human trafficking in a structured data. So that's basically is a case information form. In the second stage, we can summarize this as basically the extension of phase 1, where you facilitate the real-time data capture and ML models for the detection and identification and response capabilities by adding sources and domain and refining source ID capability. And in third phase, we use the analysis tool for monitoring and targeting operation against human trafficking in real time by focusing on the, for example, pattern extraction, tracking, and network modeling. And today we are here to talk about first stage. We can divide the first stage into 3 parts. The first part is news collector, second part is the news similarity checker, and third part is information extractor. So basically these 2, first and second part, this is an OSINT collection, and the third part is information extraction from the those collected news. The news collector, what we do is in news collector, what we do is we crawl the news articles from internet, and then we check for the similarity, because many news are similar, and we don't want to have the similar news in our database. And after when you check the news, we flag out the similar news, and then we start with the extraction process. In a very simple way, if I have to explain the architecture of the system, we have a news crawler, then we crawl the news, then we pass it to the similarity checker, then we flag out all the similar news, then we send it for the model for the CIF extraction, then we save those CIF fields, the necessary field, into CSV and database. Let's talk about news crawler and how we are really crawling the news. We're making use of 2 API, Newspaper 3K and Google News API, in order to collect news from internet. And the way that we are searching news is basically we are making the combination of 3 things. The first one is website list. We are looking for news in particular website. The country list. These are the countries that are that has the most of the victims. And then the search phrases, for example, human trafficking, girls trafficking, labor trafficking. And we make the combination of these things. For example, human trafficking, Nepal, and we search in these terms, labor trafficking in Cambodia, and we search for this term. And this is how we are curating and searching for the news articles in the internet. So as I told, country lists are the list of the countries that Love Justice focused on, as well as these are the countries that has the highest percentage of human trafficking cases. Now let's talk about the search phrases, how we come up with these phrases. So what we did is we basically made use of the language model called Keyword. And so we had a data set given the previous data set, collection data set given by the Love Justice. So what we did is basically pass those data set title through the keyword model, and we called the keyword collection, and we selected the most keywords that has been used by news articles. So as you can see here, trafficking was the one of the keyword that has been used most of the time. Rescued, women, girls, arrested, these are in the serial order of having the high frequency of those keywords in the news title of the articles related to human trafficking. First part, news crawler and extractor. So basically, we extracted the news using the combination of search pages, website list, and country name. And right now, what we are doing is when we extracted news in 3 days period, we crawled 700 news altogether, and we have set the crowns of in order to do this for every 24 hours. And right now, the news are being served in MongoDB AWS. The general time consumption is basically 7 minutes to 20 minutes for the 700 articles in order to process 700 articles. We are making combination of 12 search phrases, 15 countries, and 174 websites. So this is the combination of the search that we're using right now. The second part is news similarity checker. We obviously don't want to have a duplicate articles because it will basically miss duplicate data. So that's why we're trying to make sure that we don't have duplicate articles at all, but we don't even want to delete it completely. We're just flagging it out because sometimes the same cases, the same trafficking cases might appear 2 times. And what happened is the latter news might contain more information about the case with much more detail. So we are only flagging them out for this right now. So basically, the first thing to do is delete the duplicate articles at all. If we find some, even the article is same, or if the title is completely same, we're just deleting it out. The second thing that we're doing is we check the question similarity of titles, and we have made a scoring mechanism in order to process that. Uh, I think the best way to explain this would be the flow, this data flow diagram. So the first step that we do is, for example, if a news one, for the news one, we check the question similarity of news. For example, let's say for the title only, we check. First, we're going to process the title of the news. For news one, we find news 33, 30, 44, and 66 having the cosine score greater than 0.30. So what we do is now we kind of now look into these three news, and what we do is we basically send these news articles, the three news articles, to the IBM NLP API. Then we extract the name entities, right? And what we do is the name entity that has been extracted from these similar articles, we compare that with the news one to make sure that, okay, they both have, whether they both news contains the same uh, name entity or not. Then if so, we have made an algorithm, that scoring algorithm basically. So it says if the cosine score is 0.30, we just give it a kind of value. If cosine score is 0.40, we give it value 40 and value 50. And this is for the titles similarity checking, and these are for the article checking. In article, we compare the name entities. We check whether how many uh, person names are matched in two articles, and based on that, we have made a scoring. How many place names are matched over there, and we have made a scoring. If the organization is matched, we made a scoring. So basically, what we're doing is we're trying to look into the entities. If both articles, whether first thing, whether title is similar or not. If yes, we give it a score. Then the second thing we check is whether the person name is same in both the article or not. We also check whether the place names are same or not, and organization names are same or not. So based on that, we get the total score, and we compare the total score is greater than threshold or not. If yes, then we flag the news as a similar. And this does work. So basic, and this whole algorithm works. I'll show you the evaluation later. Let's focus on the third part. It is information extractor. So when we extract the news and after passing it to the similarity algorithm, what you do is we use the language model in order to process the news articles and to extract the information from that. Um, so model that extracts structured information from data and populate the top right field in the case information form. This is basically the aim of the information extractor. So as I told, we first filter the news article, then we pass the IBM Watson API to get the news entity, and then we pass to the rest of the system. But here are two cases that we really need to understand. The first case is that when there are news articles are really longer, some of the news articles. And here's where the problems begins. The language models are only capable, the language model that we're using, but QA, that are only able to process 512 tokens. If it's a shorter articles, then we don't have a problem. We can directly it into the model. But when the articles are really long, some of the articles are more than 1 pages. In those cases, we need to break down those articles and process it separately. And I'm going to explain how we're doing that. Then we finally extract the CI fields, and the extraction process for longer article is completely different. Uh, so how we are getting answer from the language model? What we do is we are using a BORT QA model. We pass the article with the question. For example, we pass the whole article and we ask who was the victim. Then language model processes that and gives us the answer, and we select the best answer from the model. So here, what trick that we're using is we're asking the same for same field, we're asking different question. For example, if you want to ask who was the victim, we're asking who was the victim, who was trafficked, who has been kidnapped. So we ask a bunch of questions to the model, and model gives us the score and the answer, and our algorithms picks up the best answer from those collection of answers. This is process flow diagram. This is for the this is for the shorter article that has less than 512 tokens. So news articles that after being extracted are saved in MongoDB. We gather those articles, we clean those articles, then we send to the IBM to extract the named entity. So this block being allo basically means that we're working on the language model here. So first thing that we check is whether those articles are greater than 512 token or not. If yes, we break it down into smaller articles. This is at a very top level. Then we pass it to the model, and then we get the victim names. If smaller than 512 tokens, then also we pass to the model and get victim names. Then we create the dynamic question and get the victim's age, gender, nationality, and so on. And then we save it to the CF, those CF in the CSV file. So the process that really make things complicated is this one, how we're going to process the the larger articles, right? And I'm also going to explain what the dynamic questions are. Let's first start with how to handle the longer articles. So what approach that we have taken right now is we just break down the longer articles into smaller pieces, and we make sure that the syntactical features of those sentences, that they don't break at the middle of the sentence. So we're making sure that we preserve that syntactic and the semantic of those sentences, and we feed each of those smaller article into the model to get the same answer. And after receiving the answer and score from each smaller article, our algorithm combines those answers and chooses the answer with the maximum score. And it is also best to look into the illustration here. So basically, let's suppose there was an article that is really large. So we break down the article into n parts. So algorithm decide in how many parts we need to break down the article. Then for article part one, we send it to the language model. We ask who was this, what was the age of Sita. So Sita is being the victim right now. We ask what was the age of Sita. So for article part one, our model gives us the answer one with the score one. So article part two, we send it to the model, ask the same question, we get the answer to score two, and we get the n answer over here, and then we choose the answer with the maximum score. So this is basically at a very top level how we are handling the longer articles. The other complex thing was here that where there are cases in which there are more than one victims. For example, the article could contain about the labor trafficking, and when they are doing the rescue mission, there might be more than one victims, and those names, we need to make sure that we are extracting all the names from the articles, right? So now here's the complexity begins, because the language model will only point us towards one victim name, telling, okay, this is the victim. So what we can do is now we had made another algorithm and made another approach in order to process the multiple victims. So what we do is we pass the news article to the model, then we ask the question, who was the victim? For example, we get the victim name. And what we do is that when you get the victim name, we see that whether that victim name is accurate and is presented in the entity from the IBM or not. If yes, obviously yes, so that the name of the victims, we add the victim name in the list. And what we do is that after adding the name in the victim list, we remove that name from the article. And again, we send it to the model to process the same article. So in that process order, we extract the multiple victim names from here. If it's not in the IBM list, we do other manual processes in order to find out who was the victims. And the good thing about the model is also that there are some cases in which there are names that really looks as the victims but not, because the articles were written in that particular patterns. So in those cases, we just flag the victim out. So we just flag those victims into flag victim list, so that later on the annotator can human annotator can check for those things. Now here's the complexity. So now we need to process multiple victims in longer articles. So the whole things get complex out. So because now we have a very long article. Now those long articles, however, what we need to do is we need to break down into article part 1, article part 2, article part 3, and other article part. And for each article, we need to go to the model and now need to retrieve the name of the victims. Now we process each particle here, small articles. Here we pass it to the model, and then we ask what's the victim name, and we repeat the same process here, recursive process, and we get the name of the victims. We do that for article part 2, article part 3, and so on. And finally, we combine the final victim list from here. And if the victim list is not in the IBM list, we flag them out. So basically, this is one of the things that makes the whole algorithm and the model really complex. And now let's talk about what was the dynamic question, right? So the first thing that we're asking our model is what is the name of the victim? And for example, our second field is we want to get the age of the victim. We can ask the model what was the age of the victim, right? But we can leverage the whole process in order to get the more accurate answer by creating the dynamic question. So when I say the dynamic question, what we're really doing is, instead of asking what is the age of the victim, here we are asking what is the age of the Rita, given that Rita has already been found as a victim by the model. And we just create the dynamic question like what is the gender of Rita, what is the address of Rita, what is the nationality of Rita, and so on. And same goes for other victims as well. Now, if we have like multiple victims in the article, now we create a dynamic question for all those multiple victims, and then we pass those into the, and if it's a longer article, then we pass each of those into the different, we look for the answer in different shorter article that we have breakdown. So that's the typical process flow. So now let's talk about the performance matrix. The competition in finding the multiple, so this is when we are finding the multiple victims, age and gender from the articles. We perform this experiment on MLT2 large on AWS with 8 GB of memory and 2 virtual CPUs. So basically, if you're computing short articles that we don't need to break it down, we have the average of 1.73 minutes, and the sampling was done in 116 articles. And if you are the average for computing longer articles is basically 3.52 minutes. This is for the 37 longer articles. The overall average time doesn't matter whether it is a longer article, shorter article. It's 2.16 minutes to process in order to get those CI fields, 2.16 minute. Median is 1.61. The longest article that has, I think it was 800 to 900 tokens, it took around 9.68 minutes in order to process all those articles. If we look into why that was happening, we can look into the token length of the article versus the time. We can see that when the token length of the article increases, so does the time in order to process those articles. There are few cases in which even the article are less than 512 tokens, it's still taking somewhere around 6 to 7 minutes, right? And this is because this article might contain the multiple victims. And when we have multiple victims, we're basically going into the recursion in order to access those multiple victim names. So that's what has been happening over here. We're looking into the multiple victim names. So that's why the whole recursion happens here. We're asking a model the same question multiple times. So that's why it takes a little bit longer time than the other smaller articles. We can see here that point can be validated with this graph. We can see that when the number of victims versus time. So when the number of victims increases, so does the time also. So we can see that over here, most of the victims' names are from 0 to 6 or 5. And when the victim names increases, so does the competition time also. And if we see that, okay, the victims are only 2, but it's taking a longer time. So this is probably because the article is longer in length. So we have to break it down and look for the victim's name in smaller articles as well. So in terms of the longer article, we can see that number of victim versus time. Even for shorter articles, it starts taking some around 3 minutes, 4 minutes in range. So that's why we can conclude that the number of victims and the article length are directly proportional to the time taken by the model in order to process for the CIF fields. When we check for the accuracy in the 46 articles, those are the longer articles, we get the accuracy of 65.21% in extracting the multiple victims' name. So we need to understand what was our evaluation methodology, because we really faced the challenge over here. Since we are working with the language model, the answer that we're getting is not in a level 0 and 1, but we're getting the answer in terms of the text and the string. And it's kind of difficult in order to uh, make the evaluation process automatic by comparing the uh, answer given by the model to the answer that we had in our annotated data set, because that becomes the problem of string matching, and it's kind of difficult. And sometimes what happens is the language model can give us the first name of the answer only, or in the annotation, the first name, only the first name could have been mentioned there. So that's why we had to perform a manual evaluation. And we did that by creating a very simple algorithm where we manually went through all those articles and compared the answer provided by the model by ourselves. And the same evaluation we did for the other attributes as well, such as gender, age, victims, and so on. This is a performance metrics for similarity checkers. So when we gather 200, when you crawl 252 articles and saved it, and after running our similarity checker algorithm, so basically what we received is that we flagged out 59 articles being similar, and we received accuracy of 62.71%, given that 30% of articles were in fact similar. So the question is, what happened to the rest of the articles, why they were being flagged as similar, right? So when we look into the rest of the articles, the problem with those articles is that only the title was exactly same, and the content inside the article was empty. So there are many websites that are I'll say the false website that just copy the link from the good website just to increase their website ranking. So they get the they have the same title from the good website, and but the content is completely different. So that's what those rest of the articles were. When we're trying, so this is for the victim accuracy. When we're trying to extract the victim names, we receive the accuracy of 73%, and we perform this over 103 103 articles. But this is not enough. We also need to understand what happens in terms of the number of victims, because we're not only looking in terms of the articles, we're looking in terms of the victims, right? So in the total number of victims in 153 articles that we processed was 347, and the model successfully retrieved 205 name from those articles. And obviously error happened, but why those error happen is because sometimes model confuse the name of the author with the name of the victims. Sometimes the article present the name of the trafficker. For example, article talks more about the trafficker in a way that the trafficker starts to seem as a victim. So that's why sometimes the model confuses the trafficker name as a victim, and sometimes the places names are triggered as a victim name because these places are the name of the district from from a very unknown places. So that's why sometimes those names are treated as the name, and in some cases even the relatives or worker names are treated as the name of the victims. In gender accuracy, we matched the gender in 93 articles, giving us 65% accuracy. Over here, we can see that when the overall match was 197, and the only mistake that we did was 25 in the overall gender given in the article. In some cases, there were 19 mistake was made while processing the gender for girl's name, and 6 mistakes while processing the names of the boys, because uh, and these cases, these mistakes were happening on multiple victims' name, where then only the names of the victims was given, but it does not mention whether the name is there was no syntactic or semantic relation whether the name of that was belonging to boy's name or girl's name at all. And when we worked with the gender API, even gender API was not able to identify those names, because those names were most of those names were very native in nature and very unheard of. We also process the age accuracy. We overall match was 66 match, and the mistake was 33. The problem was that when we are processing age, in most of the cases, age was not given at all, but there were some numeric value given right next to the name of the victims. So sometimes models try to predict that as an age. So that's where the mistake occur. And in terms of address, we received the accuracy of 51% in the address. I would like to talk about the system architecture, how we are currently working. So what happened is our news crawler, it is inside the EC2 instance in AWS. So and being served on MongoDB, we extract these news articles in the Amazon SageMaker, and this is where our model is. So we process those things and we save our CSV file in S3 bucket, as well as we also goes back and we update the MongoDB database itself. So we have two backup, one CF fields will be in the MongoDB and another is in .csv file. And Lob Justice or the users can extract that via FileZilla, or they can directly download it from AWS portal. Uh, Resource cost table, this is, we calculated how much it will cost in order to do the whole thing. So EC2 instance, it is basically free. If you look into this one, uh, if we're using it more than 750 hours for a month, it will be 504 per month. This is SageMaker, it's $1 per hour. IBM Watson API, it goes and analytic. So basically, I can say that for the IBM Watson API, if article is long and contain 10 victim names, this is the worst case, and this could be 10 NLU. So that is basically 0.003. Google News API is free. Amazon S3 is free up to 5 GB. Gender API costs $20 per month. So what we did is that we just break it down into the in order to process 6,000 articles. So over here we can see that when you're processing 1,400 articles a week, or we can say 200 articles per day, that basically costs us $5. And the computation using the MLT2.large SageMaker, the cost will be 216. Gender API, if you're using Gender API, 42.60, and IBM Watson 360. So when we calculate that, this is basically $623 per month. And in average, the cost for processing one of those articles is basically 0.10. So this is the cost of processing article, which is very nominal given to the cost of human annotation. We can, instead of working with AWS, we can also work with the alternative infrastructure, where the users can basically host the whole system in locally using NVIDIA 38 GPU, or they can also use the Google Cloud or Azure based on their requirement. The configurations are very changeable. They can change the configuration, what are the search pages they want in order to crawl the news, what should be the duration for crawling news. Not only that, they can also change the score mechanism for the algorithm of a news similarity algorithm, because this is basically time to time news, the writing pattern for the news gets changes, and we want to give the users the ability in order to monitor their news similarity algorithm and change the score and threshold value for the algorithm themselves. In the information extractor, they can add and modify the dynamic questions for each of those CIF fields. This is an example, so we can see that this is from the model example. We can see that the article itself here, it says the disappeared are Basanti Limbu, Jamuna Rai. These are the name of the victims. In the bracket, we have the age, and we can see the result from the model. It says victim one. This is the victim one, a Basanti Limbu. So Basanti is the name of a female. The model identified the gender of the victim also, age, nationality, address. So Kirabari is the name of the, you can see that it is the name of the district in the name of, actually it's the name of a village in a Morang district in Nepal. So it identifies that as well. So there are 6 names, 1, 2, 3, 4, 5, 6, 7 name, and it identifies 6 of them from here. Not only that, it also uh, identify what was the proposed for them to travel. It could be many things. It could be the in search of good life or in search of job opportunities. But if you look here, it says that um, the interest was that they expressed their interest to visit Sikkim. So it was nothing related to false promises made by the trafficker. So this is one of the example. This is another example where we can see that the victim name is identified. We got 2 victim names, right? When you read the articles, we can see that the person that is being arrested is Bhim Prakash Rukam Magar of this one, but here the victim is basically Rajendra Prasad Chaudhary. So here the model make a mistakes of identifying the suspect as a victim, right? So it's not the case that model always predict the right thing. There are also cases in which a model predict the trafficker name as a victim names or suspect name as a victim names. It does identify the gender of gender correctly, and this was one of the cases that I was mentioning. Since we don't have the Rajendra Prasad Chaudhary age mentioned here, but we have the name, the numeric value 2.83. So sometimes model confuse this value as the value of the age. But if you look into the Bhim Prakash Rukam Magar, it identified the age accurately over here. So model, what I'm trying to focus here is that model also make mistakes while processing those articles. So we need to be very careful on how we are processing these things. Very few interesting observation. We observed very interesting. There were interesting observation in which this is the in which the model was predicting the answer very accurately than the annotated answer in the dataset. So this was one of the article in which we have Prem Kumar Maji, and her age was 38. In the annotation, the annotated data was 35, but if you look here, the model predicting 38 as the accurate answer. So there are also cases in which model is working in a very great efficiency than the human annotators. I have the other cases here where model is predicting the age as 28, but the annotated age was 26. Um, Here, while predicting the address, model is finding the address to be address more correctly. The Palpa was the address, whereas the actual address is sorry. So the address that was in the annotation was Chitwan, but the best of the score, the model predict the address to be Palpa. And if we look here, Prem Kumari was from Palpa, not from Chitwan. This model also predicts the promises that was made to victims, because this is one of the root causes for human trafficking. What happens is most of the traffickers, they lured victims into false promises. For example, promise to marry them, or promise to travel to India or to other countries where they can have a good life, good job. So you're trying to look into what were the promises made to the victims by the traffickers. So if you read articles over here, we can see that the promises made to victims was jobs, and it kind of predicted accurately. And if the promise has been mentioned in the articles, the models does predict it accurately. Thank you. So this was basically the presentation and the how the model works. If there is any question, please let me know. Thank you so much.
Bibek, thank you very much for this wonderful presentation. And thank you for the great job you and Zishan did in completing this project. I just heard from Love Justice that they are going to deploy this as their main intelligence collection solution. And also, they have given us permission to share the code and infrastructure online for open source utilization. So that's another good news for us. At this point, I would like to open the floor to the questions from the audience. Chris?
Hello, Bibek. This is Chris. Thank you for the presentation.
Hi,
I was just
Chris.
wondering if you noted that this was looking at articles in different countries. I wasn't sure if you had any problems whenever you're parsing articles that may be in a different language or in multiple languages.
Yes, so right now we're not processing the multiple languages. When we're crawling the news, we are only looking for the languages in English. But if we are getting languages in other than the English, we're not collecting that at all. When you're looking into the website, when the search combination is happening, we're looking into the website that is in English language only right now.
Okay. Would you be able to I noticed with Microsoft Edge, I think they have a built-in system for translating things to English. Would you be able to use English translated, or would it cause weird problems?
Yes, we do have a plan in order to incorporate the other languages as well. Because if you look into the what happens in the real news world, like for example, in Nepal, most of these trafficking cases are covered by the native languages and news articles rather than the English one. So they only come to the English one if that is newsworthy. But in the native languages, the news articles are published frequently. So that is one of the our future work that we need to work on. So when that happens, we'll obviously when we need our model in order to process the native language other than the English as well. So that's actually part of the plan right now.
Okay, thank you.
Thank you very much for that question, Chris. And do we have any other questions from the audience? Praveen?
Thanks, Bibek, for the interesting presentation. I would like to go on to the slide where you have the keywords regarding your search.
Yeah.
So here mostly you have mostly related to trafficking, rescued, and everything to train your model. But whenever you have a reported cases, they don't directly report that this is a trafficking case or a rescue case. It might be reported as a missing case or something like that. So how we are going to collect those information and predict them with your model? Like there is no keyword search.
Yes. So basically, if when you say that the cases might be the article might not mention the trafficking at all, right? Yes, there are cases in which a human goes missing, and it might be in the news, like for example, 5 children got missing or 5 girls went missing, right? But the problem is that we cannot verify whether it's a trafficking or not, right? Until and unless the case has been resolved, right? So that's why when we look, and these search phrases, it's not like we are making the search phrase. We did these search phrases based on I think there were like 5,000 data set that was provided by the Love Justice. So we processed those articles, and then we came to the conclusion. Okay, these are the keywords that are being used by the news articles for the title. So that's why we started with these phrases. And until and unless the missing person's case resolves, we can't say it's whether it's a trafficking case or not. So we don't want to process that, because when you go into the, if you, for example, if you search for like girls missing, there might be like instead of 2 or 3 articles, there might be 10,000 articles, because people went on missing on a daily basis, right? And that could be also be the cases of someone went into accident and has been missing at all, and someone got killed, or someone got murdered and then they have been missing. So it will be a little tricky in order to have those articles until and unless proven to be the case of the human trafficking itself. So that's why we're not processing those kind of articles.
Okay, thank you, Vivek. And one more question. Uh, you are training the model only for trafficking, and so how we are going to prevent uh, uh, the traffic should not happen, like traffic cannot be happen out of your trained data, or how we are going to
Sorry, Probin, could you please repeat the question? I could not understand it.
So you are collecting the existing data and reported data, and you're training your model. So how you are going to apply this and stop it? Like the how do you are going to prevent the cases that are going to happen?
Okay, so the first thing that I'd like to say is that we're not basically we're not training the model at all. What we're doing is what we're really doing is we're trying to create a OSINT multi-source OSINT collector. And in order to do that, we're using the language model keyboard and the BERT QA. So if you look, so what we really need in the human trafficking for our second aspect is that we need to understand what the root causes of human trafficking, so that the NGOs and INGOs can work at the community level in order to prevent the trafficking happening at all. So in order to do that, we need a really good data set to come into the conclusion, okay, this might be the root cause why human trafficking is happening. And in order to find that root cause, what we're doing is we're collecting the structured data from all those unstructured data and the articles that are presented in the internet. And based on those unstructured data, we are using the language model to create the structured data and try to come to the conclusion, okay, for example, in country Nepal, the root cause of human trafficking is because women are trafficking in the false promise of jobs, or the men are being trafficking in the false promises of getting better life in the Middle East countries. So we're just trying to make an analysis on the root cause of the human trafficking. So we're not training the model, but we're trying to create a structured data from all those semi-structured or unstructured data set presented in the internet.
Okay, thank you, Vivek. I got it.
Thank you, Rob.
Very well. Do we have any other questions from the audience? Excellent. Thank you very much, Bibek. And thanks to every one of you who's joined us for this seminar. We are going to have another seminar next week, same time. The details will be announced via email, disseminated to the college and our colleagues in other departments. I guess that's it. Have a great weekend, everyone, and goodbye.
Thank
Good
you.
job, Bibek.